A very warm welcome to the Belgian Embassy on behalf of the French-speaking community, the Federation Wallonie-Bruxelles, and the German-speaking community. I'm really glad to welcome you tonight for this very special event about exoplanets, and I'm really thrilled to have tonight for you Professor Rauer from the DLR and Michaël Gillon, Professor Michaël Gillon from Liège University. You heard the tune. Actually, you were supposed to hear even more. There used to be, and you might have remembered the tune from the 1960s, from Star Trek. There was this famous text telling about the adventures of the starship Enterprise. That used to be science fiction. Even though we had in the meantime a spacecraft called Enterprise, many things of what happened in this science fiction in the 1960s stayed science fiction. Other things became reality. Tonight, we have scientists here that will show you and tell you in their conference that they took the fiction away from the term science fiction and tell you about exoplanets. They tell you about planets beyond our solar system. And they will tell you that those planets, those exoplanets, have become a complete new field of science because we can now study them. We can now almost see them. They got a fantastic tool with a new space telescope, that allows them now to search where no one went before, where no one saw before. The Webb telescope, even if the light information from an exoplanet travels 40 years before it reaches the telescope, allows them to see a new world. I will not tell you more. You may have heard that I am thrilled about what we are to here tonight, and that I'm very much interested in what the two professors, the two scientists will tell us, and where they will take the fiction away from the term science fiction, because this is when science ends up in books as well, but no longer in normal novels, but in school books. There is the real science, and you learn about real science tonight. Thank you very much for being here. It's a pleasure for having you. And my science liaison from Munich, Mathieu Quintyn, is also to speak, but he will also be brief, as I was. I wish you a thrilling and interesting evening with the two professors from DLR and from Liège University, Professor Rauer and Professor Michaël Gillon. And if this event takes place tonight in the Belgian Embassy, it has another reason. The reason is that the exoplanet that Professor Gillon found got a name that is directly connected to our country, better even to our beers. But you will learn more about from him. Thank you very much for being here. I wish you a very interesting evening, and enjoy the evening. Mathieu, où es-tu?
Thank you, Alexander. But you have already said, so just to introduce myself, I'm Mathieu Quintyn, Science and Technology Counselor, Germany for Wallonie-Bruxelles International, WBI, who acts as the Foreign Ministry of the French-speaking community of Belgium. The main task of my work is to support research, innovation, collaboration between the French part of Belgium and Germany. I'm also responsible for the mobility of researchers to promote the academic and scientific ecosystems. And it's why it's a really pleasure for me to welcome Professor Dr. Gillon and Professor Dr. Heike Rauer for this wonderful evening. So I have a question for you, to the audience. Do you think we have habitable planet in your universe? Can you up the hand, please, if yes? Okay. But actually, we really don't know. We have expert here. So, Professor Dr. Gillon, the floor is yours. Thank you so much.
Good evening. So I'm really pleased to be here today to talk to you about exoplanets and the quest for life elsewhere in the universe. Indeed, this has been a topic of science fiction for long, but now it's something really real, really scientific. I would start by this image. Since I'm a kid, when I watch the stars, I'm fascinated by this kind of show. Not by the stars themselves, but by the possibilities that they are surrounded by possible biospheres, by habitats, maybe by creatures that also think about, that wonder about the universe itself, and maybe are asking the same questions. And this kind of let's say, idea is very old. We've been, humans have been wondering about the existence of other worlds for millennia, but now it's really something that is part of science. And so when we think now about habitable worlds, we think about this kind of image. Unfortunately, it's just an artistic view. I can't show you a real habitable exoplanets, but we think about the possibilities that there could be out there around other stars, planets that could host habitable conditions. Habitable means liquid water and maybe life, because all forms of life on Earth depend on liquid water. But before trying to answer this question, we had a long way to go. From the Copernican revolution, we understood that the sun was the center of our local universe, let's say, not the Earth, that we had to understand what was really our world, a planet in orbit around the sun. We had to understand that the other stars that we see in the celestial sphere are other suns, but very far away. And we had to study our local, let's say, universe, mini-universe, our planetary system. And now we have a very good understanding of this planetary system. So we know that it can be divided in two parts. We have close to the sun, we have, well, relatively close to the sun, not so close as shown here, of course. We have the terrestrial planets that are rocky, mostly, and are pretty small compared to the others that we call giant planets, which are basically big ball of gas. We have the two gas giants, Jupiter and Saturn. So to give you an idea, Jupiter is about 10 times bigger than the Earth in radius, and about 300 times more massive than the Earth. So it's really something colossal compared to the Earth. And then we have what is called the ice giants, which have a big core of ice and rocks also, and which are still enshrouded by an envelope of gas, mostly hydrogen. And we've studied this planet very, very intensively, first from the ground, then sending probes, thanks to the space exploration. We've studied a lot of these bodies. We've studied also other smaller bodies, comets, asteroids, everything that is in orbit around the sun. And we haven't found a planet like ours. We haven't found what we call an habitable world in our own solar system. And our planet is really special just because of this little droplet here. This is all the water, liquid water that you can find on Earth. It's only 0.02% of the composition of our planet, but the fact that this water is liquid is critical because it makes possible life. All forms of life depend on water. If you take these cells, any cell, it's mostly composed of water. It's really the solvent of life. So in our quest for life in the universe, we are searching basically for liquid water. And maybe it's too much light. We can't find, just by the law of physics, we can't find liquid water anywhere around a star. So we can define what is called an habitable zone, which is a range of distance to the star for which water could exist on a rocky planet in liquid form on the surface. And it's very easy to understand the concept. If you go too close to the star, water evaporates. If you go too far, it freezes. And so, of course, if you make the computation of the limits of this range, of this zone, habitable zone for the sun, you see that the Earth is within, fortunately. You see that Venus is a bit too close. So too bad for it. And you see that Mars is close to the outer edge. So I would say with some luck, we could have been the second habitable planet in our solar system. And then you have the tiny Mars, which has been the subject of a lot of fantasies in the 19th century. We were imagining life on Mars, civilization on Mars. But now we know that Mars has nearly no atmosphere at all. It's the opposite problem to Venus. The atmosphere is very scarce. And it's just because Mars is too small to have kept a magnetic field able to protect its atmosphere. We think it has lost its primordial and even its secondary atmosphere. And what remains is basically a dead world. So if we want to find habitable planets, we have to look much further away. There is nothing like this in our solar system. So we have to look to the stars. What you have here, this is called the Milky Way. This is our galaxy. So it's a big structure. And when I say big, it's really, really big. We're talking about 100,000 light years in diameter. A light year is 10,000 billion kilometers. The typical distance between stars in our galaxy, in this Milky Way, are a few light years. So stars are very, very far away. Even the closest star is just one dot of light. We can't make an image that would show you the details of the star. We can just make an image that shows you a dot of light. That's it. They are so far away. If we could go out of our galaxy, we can't at all. We can't even go to the nearest star. But if we could go out of our galaxy, we would see it like this. So basically, it's a very nice spiral. A galaxy it's a bare spiral because it has a sun.
There's a sun from there here. At the centrum, there is a very big black hole, and you have plenty of stars in the arms of these spirals, and it contains something like 300 billion stars. This is our local universe. It's no more the solar system. Now we know that our sun is just one star among this gigantic structure.
So, for centuries, and even at the origin of the Copernican revolution, there were some philosophers that imagined that stars were suns and that they could have planets. And there were even Isaac Newton, the guy that basically invented modern science, thought about these planets, exoplanets. But it took centuries, basically, of technological development to be able to detect them. And the ones that achieved this detection, they are still both alive, because it's very recent. It was in 1995. They are Didier Queloz and Michel Mayor, two Swiss
astronomers that discovered this first exoplanet from France back in 1990.
And now we have more than 5,000 of them. And with such a large sample, we can draw the following fundamental conclusion. Basically, all stars in the universe
have planets. This is really something to keep in mind when you
look at the planetary system. Even if you don't see the planets, they are out there. All stars have their planets. And the planetary systems are very, very diverse. We thought that we would find systems very similar to ours, and in fact, not at all. We find systems that are extremely diverse, exotic. You have systems that are super compact. Here you have 6 planets of a few times the mass of the Earth within basically the orbit of Venus. 5 are within the orbit of Mercury, which is the closest planet to the Sun in our solar system. So these planets probably formed further out and migrated close to the star. You have giant planets that are super close to the star. We call them hot Jupiters. It takes only 3, 4, even sometimes less than 1 day to make an orbit around the star. Well, for Jupiter, it's 11 years. You have planets around binary stars, triple stars. So when I say all stars have planets, even binary and triple stars have planets, or a lot of them. You have planets that are orbits that are not circular, like the one in the solar system, but very elliptic, very elongated. We know now, when it's pretty recent, that there are hundreds of billions of planets which have no star at all, which are free-floating in space. These planets are formed around a star, and they have been ejected. And so imagine that there must be out there billions and billions of Earth-like planets that have no star at all. Of course, they are not habitable, because if you don't have a star, you don't have the energy to have liquid water and so on. You even have planets around what we call neutron stars, or dead stars, basically, remnants of massive stars. And within these 5,000 exoplanets, we have now a catalog, a subsample that is growing of potentially habitable planets. So these planets are small or low mass enough to be rocky, and they are orbiting within the habitable zone of their star. So here, again, just artistic view. I can't show you really these planets. But these planets are very interesting because what we would like to do now is to characterize them, to study them in detail, and search for traces of life on these planets. And this is something that looks like science fiction, but this is really doable with current technology. It's really hard, but doable. And one way to do it would be to take a very big telescope and to be able to make an image where you would see the star, and you would see the planets, and to analyze the light of the planet itself. This is what we call direct imaging, and this is something that was totally science fiction for centuries, and this is something that we can do now for at least for a few exoplanets. So here, it's not an artistic view, it's a real image. It's the first exoplanet here that was detected close to a very low mass. Well, it's not really a star, but I won't enter into the detail. And here you have 3 planets that are orbiting this star here. This star is blacked because the star basically has to be dimmed to be able to see the planets. And if we could make this kind of image for an Earth-like planet, what we would do, we would take the light of the planet itself, we would scatter it in different colors, in different wavelengths, and study the distribution of light in the different colors. This technique is called spectroscopy. And when you do spectroscopy on any object, you can learn about the composition of the body, of the object, especially of the outer shell of the body. And here what we could learn is the composition of the atmosphere of the planet. Even if it's light years away, the laws of physics, for what we know, are the same everywhere in the universe. So we should be able, by studying this, what we call spectrum of the planet, we should be able to find traces of molecules like you have here. So you have CO2 here, which is visible in the spectrum of Venus. You have, for Earth, it's a more interesting spectrum. You have also patterns, features that come from water and ozone. Ozone is related to oxygen that come from photosynthesis. And here you have Mars, you have only CO2, which is visible. So these observations have been gathered in the infrared, which is a wavelength range, which is not, for which our eyes are not sensitive to. And so an alien observer that would do spectroscopy of the Earth, light years away, and they would get this kind of data, should be able to say this planet has probably liquid water and probably some activity of biological origin, producing a lot of oxygen coming from what we call photosynthesis. So we could do this for exoplanets. Yeah? No? Yes. But the problem is that you take the Earth, you put it light years away, it's going to be a very, very faint object. Super faint. But now we can build super, super big telescopes. Really, really big. So even if it's light years away, we should be able to make an image to see, to get the photons, the light coming from this Earth, exo-Earth. Still, the problem is that it will be always very close to something, which is, in this case, is a firefly. It will be very close to the lighthouse, which is the star itself. And if you turn on the lighthouse, you don't see anymore the firefly. The problem here is not a problem of what we call resolution. It's the possibility to make image where you see plenty of small details. The problem is a problem of contrast. You have a very bright object and a very faint object, and when you turn on the bright object, you don't see anymore the faint one. Still, we have a good example given by nature that we can see very faint things close to very bright things if we mask the light from the bright stuff. And the example is the moon passing in front of the sun. So when it does pass in front of the sun, you can see the outer atmosphere of the sun, what we call the corona, which is a very nice thing to see, but you only see it when the moon is hiding the bright disk of the star. And so this is the basic, let's say, concept of what we call coronography, which is an optical technique to hide the object that is in the center of the field of your instrument, to see very faint objects that are close by. And so if someone could start the video, I would show you the concept of a space mission that is designed now to try to do the same but for exoplanets. So you would have a space telescope, which is here, and it would be coupled to, let's say, an artificial moon, if you say. We call this a star shade. That would be put thousands of kilometers away from the telescope, and that would only hide the star itself to show what is around the star, so the faint planets. So this is a concept. It is in development, and I think it will take at least 20 years to exist, and it will be very expensive, but this is, in theory, doable. Nevertheless, I don't want to wait 20 years to search for habitable planets and study them. So I can tell you there is a shortcut to study habitable planets, or potentially habitable planets. And it is to use methods that are not direct, but indirect methods. So you don't really see the planet, but you see the impact of the planet on its environment. And when I say environment, I mean its host star. So this is the same principle that allows you to see this invisible man here. You see its shadow, you don't see the man itself. And so what we can use, and this is a method that has been used to find most of the exoplanets, is to use what we call the transit. So in astronomy, a transit is when a small body passes in front of a bigger body. As we are on the third planet in the solar system from the sun, and they are all in the same plane, you can see from time to time the two inner planets, Mercury and Venus, passing in front of the sun as seen from Earth. So what you have here is an image of Venus in front of the sun. So it's a transit of Venus. For exoplanet, we are not able to make such an image when you see all the elements of the stars. And so we can't make an image of the passing of the planet in front of the sun, of the star. But what we can do, and with current technology we can do it very precisely, is to measure extremely precisely the brightness of the star and to see how it evolves with time. We call this photometry. And when you do this, and when you have the luck to have a planet that passes in front of the star, you will have a dimming, a drop of brightness of the star that will last typically a few hours or sometime less. When the planet has passed, the flux the measured brightness will go back to its normal level. And it will be something that happens every orbit, so you will have an event every orbit. And if you are able to measure this and to measure the frequency of the transit, you will know the relative size of the planet to the star, because the bigger it is, the more it hides the disk of the star. And you will also know, thanks to the law of gravitation, how far it is from its star. Using other methods, you can learn about its mass. So you know its mass, you know its radius, so you can infer its density. You can see it's a gaseous planet, so it's a big thing, very puffy, or it's a very dense rocky planet. And you can even learn about its atmospheric composition. You can study its atmospheric composition even if you don't see the planet. Just because when the planet passes in front of the star, you have the atmosphere of the planet, the atmospheric limb of the planet that will pass in front of the star, and it's not totally opaque. It will filtrate the tiny fraction of the light emitted in our direction by the star, and this filtration will really depend on the composition of the atmosphere. So if, for instance, this atmosphere is very rich in CO2, we know that CO2, so dioxide of carbon dioxide, it absorbs light, but at specific wavelength, in specific colors. So in this wavelength, in these colors, the planet will look a bit bigger, in fact, because the light emitted in our direction passing in the atmosphere will be blocked by the atmosphere. But in other wavelengths, where CO2 does not interact with light, the light will pass through, and so the planet, when we'll measure its radius, it will look a bit smaller. And so by this method, we will be able to decipher the atmospheric composition of the planet. And it looks, again, very abstract and like kind of science fiction, but it has been done for plenty of giant exoplanets. Still, if you want to apply this technique to smaller planets, we have a size problem, which is that I told you, I showed you the Venus in front of the sun. You see how small is Venus compared to the sun. The Earth is the same size, and you have to think we are searching for the signal from the atmospheric annulus here. So it's something extremely tiny, and with basically current technology, it's not possible to detect it. Still, the shortcut is to go to smaller stars. And by chance, the universe is full of small stars. Most stars in the universe are much smaller than the sun. We call them red dwarf. They are tiny, they are cold. And the coldest and smallest of them are called ultra-cold dwarf stars, and they are really the best opportunity to be able to study the atmospheric composition of a terrestrial planet. We just have to find the right planets that pass in front of this kind of stars. And so, now we go really in Belgium. In 2011, I decided to start a prototype survey using a telescope that was installed by Liège University in Chile in 2010. So it's called TRAPPIST. It's an acronym. It's also a reference, of course, to Belgian beers. And the goal was to observe a small sample of these tiny ultra-cold dwarfs, so 50 of them in the solar neighborhood, to see if we could detect Earth-like planet with this kind of telescope. And by chance, I would say, in 2015, this prototype survey detected an amazing system of 7 Earth-sized planets in orbit around a very nearby ultra-cold dwarf star. When I say very nearby, 40 light years, so of course, at the scale of the galaxy, it's very nearby. And these planets, they mostly have the same size as the Earth. You see here, again, an artistic view, so it's a very homogeneous system. It's also a very compact system. So the inner one takes 1.5 days to orbit around its star. The outer ones, it's only 19 days. So it's really, really super short, super compact. The typical distance between the planets is only a few Earth-Moon distances. So it's really, really compact. If you were on one of these planets, this is a kind of view you could have when looking in the sky. So first, the star, it's 10 times smaller than the sun, but the planets are so close to the star would look much, much bigger in the sky. But it emits mostly infrared and red, a bit of red, so it would look much dimmer to the eye. And the planets themselves, as they are so close to each other, you would see them like we see the moon. You would see all the details, you would see the clouds, you would see the continents, whatever. I don't know what's there, but you would see plenty of things. And this system is amazing, but so far we had done the telescope required, well, until recently, we had done the telescope required to study them. What we need to study these planets is a telescope that is very big, which is in space, because from the ground, you have the atmosphere of the Earth that blocks a lot of signals, and you want to study these planets in the infrared wavelength range, because this is where all the good signals of the molecules are, and unfortunately, our atmosphere blocks infrared. So you need a space-based, big infrared telescope, and NASA, with the help of Europe and Canada, launched such a telescope last year, and it has been now put in commission, and it's now fully operational. It's called the James Webb Space Telescope. So its mirror is 6.2 meters. It's so big, in fact, that it had to be folded in its rocket. It's an Ariane rocket that launched it. It had to be folded, and it took weeks for it to be deployed. It's not in orbit around the Earth. It's much, much further away. It's 4 times the Earth-Moon distance from the Earth, in a very good location to observe deep space. And it has started to observe TRAPPIST-1. And I can't show you, unfortunately, results, but they are pretty encouraging. Now, I told you we had this prototype to search for planets around ultra-cold dwarfs, but this prototype had only a target list of 50 targets. Now we have, thanks to TRAPPIST-1 and thanks to a lot of effort, we have a real ambitious project aiming to search basically all the nearest ultra-cold dwarf stars, and there are more than 1,000 of them, for systems like TRAPPIST-1. So it's called Speculoos. It's again a reference to Belgium. I don't know if you know Speculoos. I think it's something also that you eat here in Germany, Speculoos, a kind of cookie. I hope we will taste some today. And so Speculoos use bigger telescopes. They are, like TRAPPIST, they are robotic. So no one is there to operate. They operate on their own. We have 4 of them in Chile, in the Atacama Desert. We have 1 in Tenerife. A second one will come soon, funded by the Wallonian region. So thank you, Wallonian region, for this. And we have 1 also in Mexico. So it's always good location. And when you do astronomy, you are always in good location because you need to see the star very clearly. So it's a very nice job, I would say. This is the kind of view you can have in Chile. If you take even an iPhone and make a long exposure, you can make this kind of image because the conditions for observing the sky are much better than here in Europe. And this is so not a bad choice to put telescopes there. And Speculoos has been in operation since 2019, and we have found our first system that we call Speculoos 2, because Speculoos 1 is TRAPPIST-1 in our vocabulary. And it is composed of two planets a bit bigger than the Earth. That one is in the habitable zone of the star. The other is a bit closer to the star. So again, it's a very compact system around a very tiny star. So if it was compared here, it's compared here to the solar system. You have Mercury. You have the star here, the sun, and on the bottom you have the star itself, Speculoos 2, and you have the two planets that are super close to the star. Again, they are good targets for James Webb, so we will observe them with James Webb to try to detect their possible atmosphere and study them. And so with this kind of project, we have good hope to learn if this kind of planet around very tiny stars have atmospheres, and if maybe some of them are habitable. But also we would like the community, well, it's a general question, to know more about what we call Earth twins. So Earth twins are planets like the Earth, but in orbit around sun-like stars. And in this respect, my colleague Heike Rauer is going to talk to you about a European project that will search for this kind of planets. And I'll leave you to Heike for the second part of this talk.
We move towards the search of Earth-like systems, as Michaël said. You already heard that our solar system, as you see it here, with the small terrestrial planets in the Earth as the third planet, with us sitting here, may be very unique. We don't know. Yeah, you already heard there are many planets around. There are many planets that are different to us. We have planets that are so close to the star. They have more than 1,000 degrees on their dayside temperature, too hot to be habitable. We have planets that lose their atmosphere, planets on orbits that are going almost over the poles of their stars. And like the planets like TRAPPIST-1 around these small, cool type stars. But what we have not found yet is a system like our solar system. And this, of course, leaves the question, are we unique? Is something special with our system? Honestly, mankind normally thinks we are the standard in the universe, right? And we don't know. We don't know if this is the case. So there has been an American mission, Kepler, that was already scanning the sky for planets, and Kepler has given us statistics. Mika already told you, every star in the sky has a planet. This is something we know now, the first time in mankind we know it. And we can even say that every second star in the sky has a small planet. Small means smaller than Neptune, yeah? Planet. But if you look what the Kepler mission did, the Kepler mission survey is complete for planets with a period of 85 days. Here you have to compare it with the solar system. Mercury, our innermost planet, has an orbital period of 88 days. So we know that at least every star in the sky has a planet, but these planets would be inside Mercury's orbit if they would be in our solar system. So they are very close to their stars. And what we don't know at all is there any system out there that has a planet like the Earth, an Earth-like planet? The statistics is not there. We don't know. This would be a science conference, I would show you some scientific publications and give you the numbers. And the estimates for an Earth-like planets are between 1% and 99%, which simply means we don't know, right? So, but then you have to ask yourself, well, she tells me we are looking for Earth-like planets. What does it mean, an Earth-like planet? And a long while ago, I found a nice comment in the internet for this. Yeah. Because it's exactly that. What is Earth-like? Yeah? This is car-like. do you, if you search for cars and I give you this, do you accept it as a detection? Yeah. And then you have to, because I did cometary physics before, and I'm in the solar system community. I'm not an astronomer in this sense. And then you have to come with your knowledge about the evolution of the planets and the evolution of Earth. And if you look back, how our solar system evolved, well, the planets formed, first the sun was made, okay? When the sun was made, from the remaining gas and dust, the planets were made. And the gaseous planets, like Jupiter, they are just made out of hydrogen gas with some trace gases. And Jupiter is relatively boring. I hope there's no Jupiter scientist in the room here today, but boring in the sense that Jupiter, they just cool and they contract. And they cool and contract still today, but that's it. Compared to terrestrial planets like the Earth, where the Earth formed, it's made out of silicates, out of rock. So it was very hot, so the whole Earth was molten. It had a magma ocean. The whole surface was covered by a magma ocean. And then it cooled, and a crust formed, and continent formed, and oceans formed. Tectonics developed, volcanism developed, and the whole atmosphere changed. Yeah? The volcanism brought heavy elements from the interior of the Earth to the atmosphere, carbon dioxide, CO2. And the early Earth's atmosphere was CO2 dominated. And then, after about half of its lifetime, life grew. Life started immediately after the surface was there in a CO2 atmosphere. But then the life in the ocean produced so much oxygen that the oxygen bubbled out of the oceans and came into the atmosphere. So the atmosphere that we have on Earth today, with a large amount, 20% of oxygen, is just 2.5 billion years old. So there was a level where life developed, and from the CO2 atmosphere, the Earth went to an oxygen-dominated atmosphere. And this large amount of oxygen is a sign of life on Earth. So Earth did terraforming. Now, at the same time, the sun also developed. Yeah, it changed its energy. With time, it will grow and become a giant planet. You see, when I say Earth-like planet, already if I have an Earth twin, what do I mean with an Earth twin? The Earth twin just after it formed. The Earth twin in the first 2 billion of years, the Earth twin as the Earth is now, or an Earth twin as the Earth will be in 2 billion years from now. And then you have to imagine what would happen. Oops, this was too fast. Go one back. Can't go one back. Now, what would happen if the Earth would have had less water than it had? It would have resulted in a desert planet. If the Earth would have had more water, maybe we would be a planet completely covered with oceans. Or if we would have more continents, we would be a green planet. So you think that when we say we are looking for an Earth-like planet, there's a whole world of planets to explore, which would be similar to Earth in size and mass, like Venus is the same size and mass as the Earth, but they could have completely different evolution, and you can understand they could have completely different life forms or no life. We don't know. And this, of course, is something we want to explore, and it's a big puzzle. It's not something where you come and life waves at you. Yeah? So at the end, it's a big puzzle that requires understanding planet evolution and understanding the processes on planets. And this is also something where I say it's something we understand something about Earth as well by comparing to other planets. So now I come to a mission. We want to detect these Earth-like planets, and I told you we don't know them yet. A way to show it is this plot, and I have text here, don't care, I will just tell you, but if you like to read. This is a plot that tells you gives all the dots of small planets that have a known mean density. The mean density is important because only if we know the density, we can say it is a rocky planet and not a gas planet, right? And the green band is the habitable zone that Michael was talking about. Only planets in the green band have the potential to have liquid water on the surface. And what you can see is the Earth is the Venus, the green band systems like ours, computing empty, we have no detection. Where we have detection in the green bands down here. These are the small stars, and exactly TRAPPIST is down there. TRAPPIST is an exciting discovery, and what we will do, we will start to fill the green band up, starting from the easy cases to the more difficult cases. And so one way to do it, or the next mission in the queue to do that, is the Plato mission. Plato is a mission of the European Space Agency. It's a third M-class mission. M is for medium. It stands for, Plato is planetary transits and oscillations of stars. Oops, I'm too fast. I'm sorry. So Plato will... these are the methods that Plato are using. So Plato wants to detect the planets with the transit method. So it will take light curves of stars. But it wants to determine their radius, the size from the light curves. It also wants to determine their masses. And for the masses, we need another method. The masses don't come from the satellite. The masses will come from a huge ground-based observing campaign that involves the largest and best telescopes in the world, to measure the motion of the star that's in the wobble, we say, that is induced by the planet. And the bigger the planet, the more the star wobbles. And this is something we can measure. It's called radial velocity method. So we will get the size from here. We get the masses from the ground, but the light curves will also show the pulsations of the star. The stars are, you can imagine them as a big gas ball. And of course, that is not static. It has some, we say, eigenfrequencies. It expands and contracts. And it does that depending on its age. So we can derive the size of the planet, the mass of the planet, and the age of the star. And since planet formation is so fast, it means the age of the planet. And with this, we know what kind of planet we have, at least to first order. Yeah, of course, in reality, everything is more complex, but to first order, we know which kind of planets we have. Now, in this second part of my talk, I want to tell you a little bit of how this satellite looks like and give you a little bit of a feeling how such a mission is built. So here is the telescope. It's, of course, an illustration. You see, it is very unusual. It's not like the telescope that you've seen before, where you have one big dish, or the dish maybe is in segments, but here we have 26 cameras on one platform. Why? Because we want to look at bright stars, and at the same time we want to see many stars. And this is contradicting. When you look tonight, if you go outside Berlin and you look in the sky, where you can see the sky, and you say you only want to see bright stars, you will see bright stars are very sparse. There's one here and another one there and another one is there. So you need a very big field of view. Yeah. And if you, in a big field of view, and you also want to see as many as possible. So if you have a big mirror, the brightest stars would overexpose, and if my collecting area is too small, I will not get the fainter ones. So how this is solved here is you have 26 cameras, and for the brightest stars, one of these 12-centimeter aperture cameras would be enough, and for the fainter ones, you add all the lights from all the cameras. Yeah? That's why we have this very unusual design. So the satellite is scheduled for launch at the end of the year 26 with an Ariane 6 from ESA, and will operate 4 to 8 years. To give you a size, so these solar panels here, it's 8 meters wide, 3.70 meters high, 3 meters, so 3 by 3 meters, and then with the panels 8 meters. So it will be half of this size here. And the cameras are mounted on an optical bench. This is this staircase-like thing that then is mounted on the satellite and launched, hopefully launched. Here it is in reality, but these are not the flight cameras. One step in the development of a mission is first to check if everything will be okay. So you don't build immediately a camera that flies. You first have to perform several tests. So these cameras, although they look pretty realistic, they are not flight cameras. They are what we call mass and thermal dummies. And already it says what you test. So they have the same mass as the real cameras, and they have the same thermal properties. But inside these cameras, there's nothing. Yeah, it's just that they have the same mass and thermal properties. And this is an image that is taken by a German company, space company OHB in Munich, where they took all these thermal dummies and mounted them on a model of the optical bench and integrated it. Okay. So then, what happened with this? Oops. I'm sorry for this. I tried to go back. Here. So then this whole thing was transported from Munich to the Netherlands, to Schiphol, and then from Schiphol to ESA, to Estek in Noordwijk in the Netherlands. And you see it here. So this is an image now taken at ESA. It's the same thing. You have somebody standing here, so you get a feeling for the size of this. And what did ESA do? ESA has a huge thermal vacuum tank. So that means, do you see this? Here is this model. There again is a person standing, so you get a feeling for how big this hole is. And so the optical bench went inside, it was closed, and then evacuated, yeah, to model the vacuum that you have in space. And then they looked for the radiation, yeah? And you see here images in the infrared during cooling, and then when it was stabilized. And this shows you the temperatures of each camera, and it tells you if cameras are all the same temperature, or if it is too hot in some places where one would disturb the other. And the test was passed, and everything was fine. Yeah, thanks God. So now, how does such a camera look like? We have 26 of them. 24 we call normal cameras, and that's what you see here. So you see, maybe I do it like this. First thing that you notice is this strange golden shaped thing on the top, maybe. This is a buffer that protects the camera from radiation, from the sun. Yeah, the whole telescope, I should say, the whole mission goes into orbit around the sun, on the same orbit as the James Webb telescope, by the way, but there's lots of space, they will not collide. So the buffer protects from the sun, and then we have a tube, and inside the tube, you see what is left here, you have 6 lenses. So it's a lensing system. It's not a mirror system, it's a system with lenses. Like in a huge teleobjective, if you're doing photographic work. And so the aperture of each camera is just 12 centimeters, but with 76 of them, and so you have seen it at the end, it's a pretty big thing. At the bottom of each of the cameras here is the detector, because you have to detect the light. And it was very difficult in the old days how astronomers, to explain how astronomers detect light. Today it's very easy. It's such a photosensitive chip as you have it here in the iPhone. However, these chips are, of course, especially manufactured for the mission with special low noise, and they are about this size, and each camera has 4 of them. With these photo collecting areas, and 26 of them, this will be the largest digital camera in the world that has ever been launched to space. Yeah, there's nothing like it before. At least nothing we know about. And in addition, there are 2 what we call fast cameras. Why? Well, these cameras, you take an image, you read it to the computer, to the onboard computer, you take the next image, and so on. But for the normal cameras, we do that at every 25 seconds, but 2 of them are read out faster because they are coupled with the system of the satellite, the stabilization system of the satellite. We have to keep extremely stable on the sky. The star must always be on the same position on the detector. That is very important. So these 2 fast cameras are a critical element here. So these cameras are mounted on this optical bench, as you have seen. And to get a size, again, you see here from integration of the camera with a person to get a feeling for sizes. Now, here we see again the satellite with the 26 cameras, the 2 faster here, these are the others. What you see to the right is an image computed, simulated, taking into account all the effects that we know from the instrument. Yeah, it's an instrument simulator that is, by the way, developed in Belgium by our Belgian colleagues, and is a very important part of the mission because we can simulate what we see, and we can put in everything that we know about the instrument and then see what would be the result. So, and if something goes wrong, we can still change it. And you can see here the field of view and how it would look like in the sky. And building such an instrument is not something that one country is doing, in particular not in Europe. It's a really true European exercise. And I have put here on the map roughly all the elements all the hardware elements that are coming into the mission, from the detector focal plane coming from Spain, and the photosensitive chips are produced in the UK, but bought by ESA. The fast camera electronics is coming from Germany. The optics is coming from Italy. The structure from Switzerland, and then we have Belgium. Belgium, who gets all these elements from all over Europe and mounts them together to have a camera. Somebody has to do that. And what does Belgium then do with these cameras? Well, it sends it out for testing and calibration. And this testing and calibration is so much effort that we don't do it in one place. We have 3 places in Europe to do that, in the Netherlands, in France, and in Spain in parallel. Because this was something difficult to get in the heads of our engineers that are normally we produce one thing, one flight model, and then you produce a spare in case it breaks before launch. Yeah. Now you build 26. For our business, this is, at the beginning they called this serious production, and now it's mini-serious production, but it is a serious product. And the point here is, if something takes longer for a camera to test, let's say it takes 1 week longer, you have to multiply by 26. So immediately you have half a year delay. And you can imagine it's a huge effort to keep in schedule and to keep the tasks as they should be. So here I want to also give a big thank you to all the partners. The team involves currently about, I would say, 150 or so working on the hardware. The whole team is about 800 people. You see here our sticker with the flags of the countries involved. You can take one home if you like, outside. And I just want to pay attention. This is really a European exercise, and that's part of the fun, to work with so many European colleagues, like my Belgian colleagues, of course. So here's also another image from Belgium. I don't know if that runs. If you could click, then you would see maybe some moving. This is a camera now in Belgium on a shaker. One other test that you have to do is, do you have to make sure that the whole thing doesn't break when it's launched with the rocket? And the launch of the rocket is not a quiet thing. At the end, when it's in space, it's fine. It's just stable and flies there, but the launch is a big deal. So what do? Is they put it on a shaker and shake the whole thing and see if something breaks, right? And unfortunately, I don't have sound here, but you have to imagine a huge sound with this. Yeah, it's really loud. And this is, again, done in Liège in Belgium, where they integrate our cameras. So, well, it doesn't break, don't worry. Okay, we can move on, I think. If you click, you have to believe me, it doesn't break. Okay, and in parallel, we are already starting with the production of the elements of the flight models that will really fly. And 26 is not far away. ESA wants to have the stuff 2 years before launch, because they also have to integrate it on the satellite and on the rocket and to test and so blah, blah, blah. So we start flight model, and the nice thing is, we are a little bit behind. We wanted to have 2 flight model cameras already done this year. We will not achieve that. We will have that at the beginning of next year. But you can see here in Italy, the telescope part with the optics and this buffle, yeah, without the detector part. 4 of them are standing here, and they are ready. They are ready. Also, the detector elements here are ready. All the CCDs are manufactured and ready. And now, piece by piece, all the elements come together, need to be integrated and then tested and calibrated. And, well, That's a huge work. This is just another example from the test houses in Spain, in the Netherlands and in Spain, where the cameras are tested. This is here in Berlin for the fast cameras, also to show you how this is done. These are engineering models. What the engineers do, they build models just to test if the whole electronic design would work. And this is the simulator that simulates the satellite. I know it's just a big boxes, but if you think it's simulating the satellite, it's simulating the focal plane, it's simulating the electronics, and just making sure everything goes through. So this is where we are. Second last slide, a comparison to previous missions. So this Plato, I said we have a very wide field of view. We need a very wide field of view. And the Plato field of view here is this blue in the north, this is, and here in the southern sky. So we will observe probably two fields. And the pink one here, the pink and the green, is the field of view of the Kepler mission that some of you may have heard about from NASA. So you have a comparison of Plato's field of view to the Kepler mission. Yeah, well, this is what we will do. We now have to decide where we start, north or south, and select the final field of view and prepare the pipeline. So with this, I want to end our little journey out of the solar system and come back also to something that Michael used to start his talk. It's the fascination of the skies and the fascination of the stars, which I think is very nicely expressed in these pictures when you look in the sky, or this image of this person looking out of the spheres to see which worlds are out there. And we should not forget, you are the first generation of mankind that knows for sure planets are out there. This is such an achievement that, don't forget it, and don't forget to teach your children. This is a change of textbooks. And it's gone from imagination of the ancient Greeks and to reality. So thank you very much.